Good afternoon to all here. Welcome you all to the final day of the FDP on application of AI and machine learning in electrical engineering. I hope I am audible to all. The technical team, please respond. Am I audible? Welcome Dr. Shrikant, who is the speaker of the first session of today. Am I audible?
Yes, madam, you're audible.
Okay.
I hope I am clear.
Yes, you are also. Okay. So the participants are requested to join fast. Before that, let me take the privilege of introducing Dr. Kavira Nishikant to all the participants. Dr. Shrikant is presently an associate professor in Gayatri Vidya Parishad College of Engineering, Visakhapatnam, in the Department of Electrical and Electronics Engineering. He is an entrepreneur and has a technology firm working on medical devices where his former students are employed and are working on healthcare products for elderly people. He has to his credit over 60 research articles. His interests lie in medical robotics, time delay systems, and intelligent systems. He is a senior member and life member of several research organizations like IEI, ERTA, IEEE, ISRD, IUCEE. He is also a reviewer of popular journals like International Journal of Fuzzy Logic and Intelligent Systems of Korea, IEEE, Elsevier, Tiller, and Francis. He has organized many workshops, FDP's conferences, and is an active researcher and is presently guiding one PhD student working with the Border Security Force. He has been the recipient of ERDA Excellent Award for teaching in 2024 and has other awards to his credit. So, with these words, I welcome you once again, Dr. Shrikant, and as a as by the scheduled time, sir, now you are requested to start your session. Over to you, sir.
Thank you very much, madam. I have over 90 slides. Hopefully, I will complete as per our schedule, because this control systems applied or using AI is a very vast subject, and I'm just trying to bring a snapshot of over years of my work and what I've learned with different organizations. So I hope my slides are moving. Did my slide move, madam? Okay. So first I have to thank some of my former professors, like my former advisor, Dr. Robert McLaren. He was a professor emeritus in University of Missouri, Columbia, USA, 25 years back, and Professor Bernard, who was author of 2 control systems textbook. He happens to be a friend of Kalman, whose work on Kalman filters we normally read. So these are 2 distinguished people. I had the opportunity to interact and learn some bits of control systems from them. I'm very much thankful to them for training me on some aspects of control. So this journey is long dated, so I'll move on. So when it comes to control, okay, most decisions these days are about linked with human beings. And in the recent course I was doing, or the interactions with Professor Srinivas Chakravarti from IIT Madras through the course on demystifying the brain, there was one statement which it says, when it comes to brain science, if we separate principles from details, complexity does not disappear but ceases to be intimidating. It is like the level of AI that is entering will be more intimidating in the near future. So that is one analysis that is resulting in more thought process for the control engineers. Now, my talk as such today will be for the topics of AI and electrical engineering, and basically AI and control engineering, how we are doing automation, and then how we are helping like some parts like AI ML for helping PID tuning, what are the case studies, what is real-time system regulation, how we do to adaptive control using AI ML. So, uh, so this is a typical classical control problem, which many people are familiar with. If you look in the left corner, the topmost where you have a control block, you would have a plant, you would have a controller, you would have a feedback element. Now, with AI, what happens? This particular controller will be a AI tuned PID or maybe a some controller. And in the feedback loop, instead of having a regular feedback controller, you would have a AI based feedback controller. So that is how the implement would take place. So if that is the case, and how we are trying to tune the plant, and how we are, want to obtain a particular desired response is what is of interest for us. So that is from a control engineering perspective. Now, where does this journey start with? As such, if you remember, the journey of controlling anything or making something or making things to start with hand tools. Then we had power tools, and then we had fixed automation as one aspect, and then we were having robotics, and then today we are in the era of intelligent systems. So this era of intelligent systems is where we are mostly relying on AI, which is helping us with automation and time saving procedures. So if you take a typical example of a loop that I'm talking about, like for instance, a mechanism where we are trying to take a decision, and if you try to give a control block diagram, you can just see how many things are going to decide. Like for instance, when you have to apply a brake to control your vehicle. So it is not the basic observance that of that of a vehicle that will decide what you have to do. It might be like what are the circumstances, what has come, like what is coming as an interference, or maybe what is the outside information, what is there inside, and uh, what are some of the orientation. I mean, some decisions require some analysis synthesis, or the heritage will help us decide. So the process of decision making as such is complicated when it comes to humans itself, and this involves a lot of time consuming aspects, which when we impart AI would be more of a complex dynamic system. So for instance, if you take this image, here you can see the monkey learn, right? So what is that monkey doing? Is it using AI? I mean, we are seeing that this monkey is not as such using AI, but it is just typing the typewriter. Now, if we have to train the monkey to use a keyboard, how is it that we do? Do we use AI, or do we teach it with some kind of technology tool? How did human learn typing, and how do you teach that to a monkey? So these are like things when it comes to some aspects of AI. Now, let us say we take the aspect of data mapping with AI. Okay, for instance, here you can see a small joke where a doctor asks a old person how his memory is holding up, and he says he has to put a tag of wife on his wife's forehead in order to understand how good it is. I mean, that shows the problems. So these kind of problems are what have to be controlled or to be solved with our AI. Now, this is one aspect of my research, which for because of which we are doing some projects, and then how it is related to electrical engineering. Now, if I take this example of a conjoined twins, okay, so two brains, and we have one body. So which brain is sending the signal, and which brain's signal has the body has to obey, or which is controlling the body? What brain is controlling the body? Now, this is the control, the complex control system. Okay, so if we are taking the complexity, the analysis, now this is a difficult problem that have to be solved. Okay, so if we are integrating AI, maybe we can solve some problems for situations like this. Now, how do we coordinate this? So it would be like you would have to understand most things are being interfaced by taking something like a brain computer interface and then human computer interaction, man machine interaction. So typically how we take the BCI interfaces, or like we take the signal acquisition and then we process it and then we command. This is like one type of control that we are these days people are interested in. So if we the past 4 days I was listening to many speakers because I didn't want stuff to overlap. So we have seen topics on load forecasting and then generation forecasting that were discussed by speakers from different parts. And then we have learned what is AI, what is ML, what is neural net, what is deep learning. Okay, but I've seen not many have gone into depth of what is called as an expert system, which is a requirement for control. These days, more of expert system analysis is what is the need of the hour, which is prompting us to learn this AI related control engineering. And then if you see, there are some extensions to this, like the computational intelligence aspect and fuzzy logic, which are another wing of the same research that people do. Now, what we are enabling, what technologies get enabled with AI is like we have to have vast amounts of data. So this is like the big data era where you store information in cloud and then you access it for taking a timely decision. And that data mining has to happen. So this has given us to evolve into data science engineering. So that is another dimension of the control engineering, because a control decision has to happen only with a proper access to data, which is mined or accessed or extracted at the correct time to analyze. So if we are seeing at the entire arena of intelligent system, which we are doing, so basically we are having overlapping circles of fuzzy logic, computational intelligence, machine learning, AI, deep learning, expert systems, data mining, and all. So so people work on different aspects, and then we try to understand. Okay, so as such, the field of AI is about planning, learning, problem solving, and it is just expanding. So we have heard speakers in the past 4 days talk about something like supervised, unsupervised, reinforcement, semi-supervised. Okay, so there are recent research papers where people are talking about federated learning. It is like training AI without sharing raw data. So more of another dimensional aspect of the AI component. So typically what we see is we will have a objective which is to be achieved with the different training algorithms, and we try to see what is the time scale on which we are achieving that, and then how much time each is responding, or what is the optimal way to reach the particular goal. It has been one aspect of learning. So as such, AI in electrical engineering, like basic analysis we have seen, like in the aspect of load forecasting, or maybe generator forecasting, as we have seen in the earlier days, last few days. So there are like the product-based engineering, because AI being used for some innovative product. So when we talk about innovative projects, some smart refrigerator, air conditioners, microwave oven, rice cookers. So how we make them smart with the AI part is something that is evolving. So they say AI brings the heavens to the world, based on one of the statements of one control expert called Michio Sugino on control. And then some people have said fuzzy is like William Kahn says, fuzzy is the cocaine of machine intelligence. Now that might be replaced by somebody saying AI is like the cocaine of machine intelligence, which will lead it. Okay, so with AI, what we do is I am the best. We try to update the best, or we keep updating to become the best. Okay, so it is like one of the eminent persons, Booth says every system is its own best analog. So when we say analog, what we try to build, how we try to make it the best. So that is what is the system level modeling. Whenever we are having a system now, when we talk about a control engineering, before we talk about a controller, or before we talk into the control engineering aspect or the feedback, we have to also understand the system level modeling and how AI embeds into the principle of I'm the best and I update to remain the best or make the system the best. Okay, so we have to understand the adaptive nature of AI and how we can use it for optimization, for intelligent automation, or for controlled or regulated automation. Okay, so this is like if you're taking a circuit design. Okay, so how best we can understand the RLC circuit and how we can make it better. Okay, so that is one way to look at it. So what is important when we are doing control? Okay, so when we are doing control, we have to understand AI used for abstraction and AI used for accuracy. So abstraction is like understanding the system, and accuracy is a precise. I mean, we are trying to get the exact result. Okay, so traditionally, if we are talking about a classical control mechanisms, these are rule-based symbolic AI, which were defining what is the problem, what is in reality what is happening, and we are trying to interpret it with the abstraction. So that was what the traditional AI or AI abstraction was doing. With the modern AI, we are improvising and we are using something like deep learning, which will improve the accuracy, and we are modeling complex systems using vast data. Okay, which is like maybe a data in cloud or maybe somewhere it is stored, and we are trying to access it, and then based on the earlier philosophy that we have understood, we are trying to make our own best analog. So that is what we are doing with this particular AI in control. Okay, so when it comes to AI in control, if you go a little bit deeper, it is like they always say that the devil is in the details. So AI excels in capturing nonlinearities, hidden dynamics that are difficult to model analytically. So it is like when we are analyzing a complex dynamic system, and if we are trying to understand the system as such, so AI will help us understand the very intricate aspect. Like in the classical control, what we were doing with the frequency domain analysis in place of time domain analysis. So whatever we could not achieve with the time domain analysis, we were doing it with the frequency domain analysis. Now, whatever we cannot do with the frequency domain analysis, we can do it with the AI-based analysis. Okay, so that is like the extension. So when we are talking like something like a fractional order system analysis, it can approximate such behavior with learning properly based on the learning of AI rather than the classical methods which were used for calculating a fractional order control system. Okay, so traditionally we are like about 25 years back, maybe I've used what is called as the system identification method using neural network models, and we were trying to train neural networks for control of a inverted pendulum. So inverted pendulum as such is a classical control problem, which is like a test bed for using any control or developing any control strategy. Now, identifying the system, understanding the system, there were tools with different softwares like the Box-Jenkins model, which were used for understanding and interpreting and developing a system model and then trying to control. So that was like the classical control where you integrated the neural network aspect. So not today, but 25 years back itself. Now with this, what are we trying to achieve? What we try to achieve is automation with AI. Okay, so it is like whatever human like cognitive abilities are there, like the pattern recognition. One of the example madam was showing the other day in the earlier lecture, or if we're trying to have a AI driven automation to mimic human intelligence, and how we are doing. Okay, so the self-driving car. So the one of the important aspect of self-driving cars navigation is the control of the vehicle. So how well we are controlling the vehicle is a very important step in order that we'll be able to do some justice. Okay, so as such, if we try to define control engineering with AI, achieve accuracy and precision is one aspect with AI. So what we could not do with the classical control mechanism, we can achieve with the accuracy and precision can be done with the AI. And then 100% automation. Okay, so normally what happens, the ratio of automation would be defined based on how much manpower we require and how much machinery we are using. But complete automation, like the dark factories that are there in China, so maybe we can go with the dark factory concept if we are able to 100% automate with AI. That requires something like a safety and security issue. Okay, so because as such, when you're talking about a control process, this control process as such may be safe, but it might not be secure. It might be secure but not safe, safe and secure but not be precise, or safe, secure and precise but not automated. So these are all like the dimensionality of a control program. When you're talking about a control, what we try to control will have different dimensions, and all these dimensions have to be analyzed. For instance, if you're talking about a circuit breaker, if you're talking about residual circuit, current circuit breaker, and how when it should operate, and what will happen if somebody has bypassed it. So it is like the safety aspect and all, and how we are actually trying to understand this. So these are like the objectives of control engineering, and how we are trying to incorporate AI into the control engineering, guys. Okay, so one of the important things when it comes to automation with machine learning for proper control will be how we can define a control law, how these control laws are constrained with machine learning. So when I say that, what does that mean? So traditionally, if we are talking about a control law might be a linear law or a non-linear law, and then we try to define it based on a pole location, or maybe define the control loop. We see the output characteristic, we see the time domain specification, or maybe a Bode plot, and try to understand it. Now, whatever we were trying to do, the same thing, the control law are constant with machine learning. It is like you define the envelope, the boundaries or limits will be established by the AI, and then we train the algorithms, and then we do it. Okay, so as such, if we're talking about an industrial automation pyramid, which is like very important, and the basic level of the automation pyramid would have sensors and actuators, and how the sensors are integrated with the actuators, and how the actuators are controlled is one key aspect for the hierarchy of an industrial automation pyramid. So our simple actuation tasks have to be precise, accurate, safe, secure. Okay, so there are n dimensions that have to come into picture, which will make the industrial automation pyramid correct, and then we'll have a product at the user end. Okay, so as the topic is more of controlling, I thought I just will give you an overview of what is happening, and then come into and narrow it down to some particular examples or case studies. Okay, normally, if you try to do a PID control, okay, as such for a plant or process that is defined, one way that we can achieve that is by using an op amp. Okay, so operational amplifier are normally used for doing a control aspect, like whatever PID control is there. The physical realization of the PID control can be achieved with the help of a device like operational amplifier. Okay, so when we talk about a device which is being used for as a controller, and we are trying to develop or control a complex dynamic system or any system, the device limits and how we can control the device parameters are some key aspects. Okay, so like how we are developing the circuit, and then what are the conditions under which that particular circuit is operating, or how the voltages are changing, and how we are defining a particular gain value based on the resistance, like RF by R would be something like a proportional gain. Now, if I'm defining the physical realization of a circuit with a op amp, and if I'm trying to achieve that value of RF by R correctly, there I might have to use a pen and paper and calculate it, but that can be done with your AI. So that is the advantage. Okay, so when you're the number of devices increases, it is like they say most controllers can be replaced by an operational amplifier based control mechanism. It is like you can build your control circuit using an op amp. Now, if you are using n number of op amps, and then if you are trying to define the ratios of RA, RB, RC, or RL, which are used as a controller in a particular circuit, how do I define these values is something that is very much important. And this is where the learning all the algorithms that we have used earlier can be imparted. So typically, where again, the important, why it might be important to be accurate, because these it could be used for a electrocardiograph amplification value that is being measured, or maybe something else. Okay, so different kinds of signals for different instrumentation amplifiers for different analysis based on the requirement. So application specific, the control circuits vary very much. And then the requirements on how we are taking the values would as such be very difficult, and as such have to be very accurate, because if you are trying to do some measurements, they have to be accurate. Okay. And then if I try to integrate it with some other transducer, normally it is like a controller, and then we have a sensor, which is like a piezoelectric transducer, which is used to measure force, pressure, or acceleration. And then we are generating an electric charge, and then we are trying to understand. Okay, so if we define this op-amp circuit for a piezoelectric transducer, and then if we try to use this, okay, for some kind of a block diagram where I'm using a PID controller, where I have the sensors and the output process, how we achieve is what we can see. Okay, now this again might appear very simple, but the signal conditioning and how, as I've mentioned earlier, how we are fine tuning the value using AI would be a difficult task. Okay, so this is one example, like a classical method of PID controller, and the physical realization using analog, I mean analog sensors, and then we try to evaluate. Okay, so how we adjust the KPKI KD values, and then if we are using different mechanisms of control, how we are using a relay-based control or a big bang control or different mechanisms, how we are achieving the values or how we are tuning the PID is something that has been a trouble for many years, because the PID tuning will be done maybe in a simulator or maybe some kind of analysis on paper and pen and paper, and then they try to evaluate and then see how the typical response is there and how the energy is varying over time. So if you are trying to take the example of an RLC circuit which is oscillating, for instance, okay, so how we are fine tuning it and how we are fine tuning the gain values and how we are applying that voltage. Okay, so typically it is like the frequency plays a very important role here, and then how, if I'm taking a capacitor voltage cycle, how it is changing is one important thing. And then with the variation in frequency for the same input, what is happening with the discharge cycle. These are things that are applied if you are taking something like a battery management system in an electric vehicle, and how the input and the output of each of these waveforms have to interpret it is something that is very important. Now, as such, when you are talking about PID controller and then op-amp based PID controller, we are talking maybe about using the combination of op-amp with the different resistors and capacitors, and how we define the control. So as such, when you are building this, so what comes into picture is like maybe a analog PID circuit, the plant, the sensors, the analog to digital converters, whatever is the microprocessor or the controller that is used in the DAC boards or any digital to analog conversions. Okay, so the challenge lies in how AI can be used for tuning the analog PID. Okay, so excuse me. So we take the plant's response, and then how we digitally adjust the analog components is what we can see here. Okay, so as such, the AI algorithm, whatever the n number of algorithms that were discussed in the previous few days. Okay, so they can be used for constituting or narrowing down to a good tuning. This could be like we can minimize the overshoot, settling time, steady state error, combination, or maybe the integral error. Excuse me, and then run the plant with various PID settings, okay, and see how we are collecting the data, and then we can use that data for training the uh, plant, okay, training the controller as such. Okay, so excuse me, just 1 second. So as such, the AI techniques, if we are talking about, so something like a AI agent interacts with the plant, and then we set up a set of rules, and then based on the rules, the error is calculated, and then we optimize the PID. So this is like a reward-based analysis, like the reinforcement learning, and then we can add different aspects of intelligence, like the genetic algorithms or naturally inspired algorithms, and then maybe use a combination of fuzzy particle swarm. There are a lot of research papers these days which are using different combinations of neural networks, which are using different aspects of PSO, because PSO, these are like naturally inspired algorithms which are basically optimized. And now whatever we do, this algorithm, we use it for tuning the controller. Basically, we are making the AI more smart. Okay, so that is what is the aspect of analysis. So when it comes to the tuning process as such, we take an initial exploration. It is like the data set that is available. So maybe some data set you take, and then we acquire the data. The microcontroller reads the sensor data, compares it. Like we have seen yesterday, there were some examples of which were applied, which can be used as a reference. So basically, we take the we may, ensure that the AI takes the decision, and then any adjustments are there, that is done, and then the iteration process continues, and the plant operates as per the desired response. Okay, so model-based AI tuning. As such, what we do here is we try to develop a plant model, we simulate and tune, and then we translate to analog component, and then we have the hardware implementation. So as such, all this can be done with different tools. Okay, so how we develop the plant model, maybe you use some kind of identification technique, and then we do it, because in most complex control analysis, you don't have a plant model, and then you might have to use a system identification where you study like the input output patterns, and then based on which you develop the plant, and then we try to simulate it using a simulation tool, and then maybe we translate to analog components. There is some crosstalk. Excuse me. Organizers, can you please mute other speakers, please? Nabimita, madam, can you mute other speakers? Okay, thank you. So whatever I was talking, basically, if we are trying to bring it down to a block diagram, as such, we would have something like a manipulator or a robot arm or any automated device or machine that is working, and then we would have a process. We would have a machine learning. We will have optimization, and then we'll have the control process. So typically, this is what we do with the control engineering. Okay. One important aspect these days, at least in because control is an important parameter in industries. So we apply it to programmable logic controllers. So these are like one aspect of monitoring a machine. Okay, so after which we can apply something like a deep learning and then take data-driven decision. Like if you are manufacturing or you want to change the thickness of the sheets that are being manufactured, or let us say some kind of a sheet manufacturing industry is there, and you are trying to automate the control process there, and the thickness have to be varied by AI program. Let us say for every 100 sheets, the thickness have to be varied. And then if you are trying to automate it, maybe there you have to apply like something like a programmable logic controller, which is like one aspect of learning. Okay, so now traditionally we have machine learning and deep learning as such by CNN. These people might have seen in the past few days. So just quickly, if we are looking at these particular aspects, as such, we have learned about machine learning, and deep learning as such would have something like self-learning, and then we tune how we tune actually will differ. Okay, the self-learning aspect is what makes the CNNs more powerful, okay, which are applied in a control process. Okay, now how we can use the big data, and if you're trying to apply something like a PLC for a process control, is one aspect of research that is prominent these days. So that is the reason I thought I would bring up some slides on that. And then people are doing something like data learning for PLCs, and how we can use PLC to be more powerful, because classical relay-based control as such might not be efficient in all cases, and maybe a PLC might be a effective alternative to deal with a machine that has to be controlled, and we can optimize it by using something like a machine data. So smart manufacturing, robot grasping, predictive analysis, smart traffic case systems, these are some aspects of deep learning for the PLC aspect. Okay. Then when we talk about as such the smart manufacturing, we are talking about smart factories, and even as I was quoting earlier, the dark factories, for instance. Okay, so it involves a lot of decision making, and then how we complement the physical science, and how we try to understand, interpret, and then develop a technology. So as such, that is a difficult aspect that we have to understand. Okay, so as such, if you try to understand the players who are involved, okay, so this is a very big process as such. Okay, so if we are talking about data, if we're talking about a knowledge, and if we are talking about something like the insights that we have to take on data, how we have to clean the data, because as such, when we are having data, and we are taking decisions based on data, and if that is defining as a control aspect. One simple example here we can take. So the coordinates of placing a mirror on a automated vehicle. So if it is based on the coordinates, so let us say a automobile manufacturing unit is assembling a car, and then the mirrors have to be placed just in front of the first what I would say, like the window. So instead of placing the mirror at the first window, if it places the second window, just because the conveyor has moved, whatever assembly conveyor has moved by 2 inches. So what happens? So it is like a flaw because of one small error. So this control aspect as such would be like controlling all in tandem, and then ensuring that we achieve the target. Okay, so the objects, equipment, processes, people, environment also all will play an important role when it comes to control engineering, and this is like a aggregated big data. So when we are talking about this as such, it would be like smart connected products, enterprises, external devices, disturbances, which have to be analyzed descriptively, diagnostically, predictively, prescriptively, and then we go with the manufacturing with the AI. So as such, this involves a lot of process in automation for control with AI. Okay, so the smart manufacturing as such is one aspect. So data-driven intelligence and how we control it, and then where we apply it. Because my talk is mostly on the control aspect. This control where we apply, we control with AI. Where do we apply? Is the control engineering in process industries is what we do. And then here, if we are trying to see like what are the key aspects of that. Okay, so if I'm talking about a robot or a SCADA system that is being controlled, how my deep learning models will help me. So at the basic level, if my device or my sensor or my actuating device is being used, and that has to give data which is stored in a machine, and then it has to be processed by a PLC or a SCADA, and then how I take a decision for a robot arm to move. So that is like controlling the arm. So how good is that? And what are the controllers, like if you are using a simple controller like PID, or maybe a complex H infinity controller, or maybe any other controller. So how the decision is taken is something that involves a lot of research. Okay, so as such, when we are using this, the malfunction detection using something like neural network, for instance, is one aspect. So when will we define so what is the problem and how do we understand it? Okay, so these are some important things. And then if we try to extend it, so for instance, something like the neuroadaptive control. So this is like some work that I've done like 20 years back by when I was in US. So basically taking a nonlinear multi-layer network, and then we adapt to bring the fine tune the weights. Okay, so these are like fine tuning with AI would be more smarter these days. So for instance, this is a snapshot of some of the research that we have done at that time, where we are trying to stabilize a double inverted pendulum, which is like a test model or the base model for fine tuning what is called as a I mean, double inverted pendulum. You have as a test bed used for fine tuning something like the missile vehicles and all. Okay, so how do I reduce the training error, and then this has to be optimized with the particular system or with my AI training. Okay, so when I'm talking about training error and how I can reduce the training error is something that we have to understand. Okay, so as such, another dimension is like the machine vision. But in the interest of time, because we just have like 20 minutes, and I just skip some things, but vision. Okay, so as the machine vision with the deep learning is one important aspect. Again, when it comes to the control aspect for fault diagnosis, and then when it comes to different industries like the aircraft engineering or chemical processes or wind turbines and all. Okay, so simple examples where we go in is like robot object grasping and how we can adapt these control techniques, and then how we do it for the predictive analysis for defect diagnosis and all. And then uh, whatever data that we have, like how we can extract and how we can abstract. Also, the classification of data is very much important, and how we can do it in the best possible ways is one important thing that we have to understand. And then what are the processes that that are involved. Okay, so I'm not going much into the machine learning models for classification. Like we have done in the past 2 days, speakers have spoken about different learning algorithms. So you can use anything based on what is the data set that you're trying to handle, and what is the industry that you're dealing, and how we are trying to analyze it. Okay, so there would be like the steps as such to perform machine learning would be more or less same, irrespective of the the algorithm that you are using. So you basically collect data and do the feature engineering, and then train your first model, and then tweak it for the analysis. Okay, and then like the data collection and separation, or what we have to do for the data pre-processing and how we have to do it. Okay, so these are like traditionally how we have been doing data analytics is something that comes into picture here. And then that is something that will be used in our engineering. So I'll skip some parts here. And then one important aspect that I just wanted to touch upon, what basically is the domain where AI will be helpful. Okay, so the effective disturbances in control. Okay, because identification of disturbances is something that is not easy for a control engineer. As such, in control engineering, you might develop a robust controller or maybe a adaptive controller, but you might not be able to identify the disturbances that might pop in. So these kind of disturbances that might come up might have to be analyzed with AI. Okay, so the mitigation of disturbances and how to identify the disturbances. So the solution to this is your expert system. That is like the goal of control engineering, where you have an expert system which will do the control part with AI without troubling the user. Okay, so that is like the effect of disturbances, and the solution will be yielding a expert system. Okay, now when it comes to the expert systems as such, is a knowledge based system, and it basically employs application domain used on interfacing. So basically needs and what is the human competence, because when it comes to industrial control processes and all, historical data is very much important, and then based on the historical data, these expert systems can come up with a solution to solve the real problem, which require as such a specialist human expert, which can, I mean, like the decision, like emergency, if there is a machine failure, what has to be done instead of the human being taking the decision. Maybe an expert system can take the decision. Okay, so what is it that we achieve with it? We achieve something like enhanced productivity, augmented work process, and man hours can be as such saved. So basically, most of these technology developments that we are doing, as such, will help us in reducing the man hours, and then fine tuning our mechanism such that we have some time to ourselves. So there are, as such, these days many companies which are using different expert systems, or they have like in China we have the freight train systems, and then there are electricity market forecasters, there are rule based engine for mobile games, so different aspects. Okay, so the conventional systems and expert systems, there is always a comparison, and then how we actually build these systems and how we can use it is one aspect. Okay, so like the conventional system mostly are algorithmic, and then expert systems as such will be heuristic, and then they represent the usage of knowledge, and then how we actually represent the data is what was conventional system. Like you are taking a classical control mechanism, you are actually plotting some data, and then you are trying to analyze what was the energy used, or you are doing calculations. Okay, so all this can be exported, as such exported to AI now, so that the expert system will do it. It will deal with the qualitative analysis, and then it will improve the effectiveness of the code. Okay, so that is what can be achieved. So as such, the huge amounts of data that are there in industries, for instance, the 24/7 operating industries, as such, will have huge amounts of data which can be used for training the expert systems and making sure that human intervention is as such reduced. Okay, so these are like some slides where I was just saying about different features, like how human expertise will define and expert systems are doing. Now, conventional systems had humans interpreting the classical controller uh, and analyzing it. Okay, so the expert system with AI would as such define and understand that particular data, and will be able to guide us for achieving the required target. Okay, it is like even when you're talking about sales or any control aspect of a particular, because in any industry you would have n number of control parameters. It is not like only the machine control is there. Okay, so it is about controlling many aspects, and these expert systems will as such help us. Okay, so so once we talk about this structure of expert system. Okay, so again, this the control engineering, where we are being driven. We are having a user, and we are having a user interface. We have an inference engine which have a knowledge base, and then there will be a knowledge engineer, or maybe as such a traditional engineer who would acquire knowledge from different sources. You would take advice from human systems, and then we would develop an environment or a control strategy. So the development of the control strategy as such is what we are trying to do it with less human hours here. Okay, so that is what we are doing when we are using AI. Okay, so the conceptual architectures and how they get modified is some important aspect. Again, this is a important on what are the players, or who are the players in the control structures, defining the control structures if you are talking about a complex system. Okay, so the architecture, what is the input, what is the output, and what is the knowledge base, how we are using it, and how we are controlling. Okay, so one of the last things that I wanted to talk uh, was expert system with AI for system regulation. Okay, so when I say that, so the system regulation as such is about uh, the ability of a control system to respond to inputs and disturbances within a fixed limited time, and ensuring the stability. Okay, so it is like an anti-lock braking system. Okay, now you all know that these days the vehicles are very powerful. They have the anti-lock braking systems, and the drivers are well equipped when to apply brake and then how to use it. But where these expert system can help us is like it will tell us when to change the brake. Okay, so the usage patterns of the brake by the drivers can be analyzed by the AI, and then that can use as a data set for developing our anti-lock braking systems, and then ensuring that we regulate the wheel speed, and then ensuring when to change the brake. Okay, so this is like one aspect. So which I thought might be helpful, because that is a future research problem where people study the brake usage patterns and with AI, and then the AI captures the usage patterns of the brakes and then develop a mechanism to indicate or give us a suggestion. Okay, the brake might not be able to control the vehicle at that particular instance, and then you might be able to tell that the AI will tell, okay, so they in the next 15 days, you have to change the brake based on your usage pattern. So that is like the target of control engineering. So if I'm taking about a vehicle being used by a human, and the human knows how to use the brake, but he doesn't know the wear and tear of the brake. So the AI will assist and help us understand when to change the brake. So that is what is one example of what we are trying to do with an expert system with AI developed for control engineering or applied to the automobile or any control aspect. Okay, so in the conclusion part, what I basically want to tell, control engineering have some advantages, like the problem identification could be speeded up with AI, because abstraction can be done with AI properly. Because when you are defining the keywords, the AI is able to tell, okay, these are the existing problems, and this is how different companies are able to solve it. So engineering solutions as such can be developed. We can improve the accuracy and precision, as I'm talking about some of the examples like the PID controller tuning and all. And then we can also develop expert solutions which will mitigate the disturbances with AI. So these are some aspects. These are some of my references that I have, like some research papers that I have studied and over the period of time. And any questions, please? I'm done. I think we have like a few minutes left, around 9 minutes. Somebody have any questions? Maybe I can take it up. Thank you.
Participants, if you have any questions, you may also write in the chat box.
I see the chat box. I don't see any questions.
Yes, so there is one question.
Can the model be considered as a twin? The digital twin concept is one of, yesterday, Madam was speaking about the digital twin applied to electrical engineering. So this is one key aspect people do, like when we are studying about a aeroplane simulator, for instance, maybe use a digital twin of an aeroplane and try to train it with AI. So there are some research papers, maybe people can refer to it. But haven't done much work on the digital twin aspect. But that is more for applied for condition monitoring of a particular system and pre fault analysis.
Any other questions from any other participants? So if there is no further, I think the participants can contact you over email if there can be questions later on. So
okay, 1 minute, somebody.
1 minute. Is the model system specific?
Is the model system specific? See, as such, you have to understand when it comes to, at least when you do it, when you study the system from a control engineering perspective, you always have to consider the system is very dynamic. It is a dynamic system which is evolving, changing, which is subject to disturbances. So you cannot say this is very much specific. Okay, I mean I have two different motors. Will the model be same for the two? Okay, I would say the model as such might be different, but as such AI will give different solutions for the two different motors, because your wear and tear of each motor will be different, because how much usage you have done for one motor will be different, and how much you have used in the second motor will be different. So your model prediction might be correct, but it will be accurate only if you are feeding the usage patterns of the motors to the AI individually, and then you use it. Okay, R and L values will be different for the two. So as I mentioned, so what is the usage pattern? Now, if I'm trying to tune the R and end values, okay, if I'm trying to tune the R and end values, and if my usage pattern of the motor one, I have used like maybe 100 work hours of the first motor, and then I have used only 20 hours for the second motor. Now, my pattern as such might be influenced, because the heating up of the components will define how precisely. Let us say you are trying to stop the machine or the motor in 2 seconds. You want to stop something in 2 seconds. It might take actually 2.5 seconds. So there is a fractional order difference that might have to be tuned, and that can be achieved with your AI if you are tuning. Okay. So approximate control, you will do it. Okay. So, but precise as such. If you're trying to stick on to some precision, okay, so if I have to deal with precision, it might have to be trained separately. That is my inference. Maybe people might differ, or there might be different ideas. I hope I'm clear.
So, thank you, sir, on behalf of the organizing committee of both AMIEE Association and Heritage Institute of Technology Electrical Engineering Department. You have given a lot of information in a single session of today. So, looking forward to more such sessions with you in our future programs. Thank you, sir, once again.
Thank you.
So, our next speaker of the second session is Dr. Jhumare. Are you there, madam?
Yes.
Okay, so let me take the privilege of introducing you first. Welcome, madam, to the final day of the session.
Yes. Okay.
So, madam, let me take the privilege once again of reading out your profile. Dr. Jhuma Ray is presently the Assistant Professor of the Department of Engineering, Science and Management from RCC Institute of Information Technology, Kolkata. And she has obtained her bachelor degree from Calcutta University, completed her MBA in finance, and is a fellow from the Indian Institute of Management, Kozhikode. She holds a PhD in portfolio management with meta heuristics from National Institute of Technology, Silchar. She brings with her over 21 years of experience in academia and 2 years of industry exposure. She has achieved Outstanding Woman Research Award in 2025. Congratulations, ma'am. She is a winner in Portfolio Management Research category, Venice International Women Awards 2025. She has also obtained Best Paper Award for contributions to intelligent financial systems and optimization techniques. She has also obtained the Best Citation Award for excellent achievement in delivering presentations. She is a regular contributor to Delhi Tech Times and Re-Atal USA on fintech innovation, AI, and digital transformation. She is a selected speaker at Ideaton 2025, and she has an ongoing collaborative research under the Balak Brahmachari Research Society, and she has featured Josh Talks. She has featured as Josh Talks speaker, and she has given very inspiring, inspirational talks across all disciplines. So We welcome you once again, madam. And now over to you, madam. The session is
Thank
yours.
you. Yeah. So thank you, Navamita. Navamita, well, she is also a Bengali as myself, and both from West Bengal and Kolkata. Navamita right now is in South Bengal, central, yeah, Kolkata. Myself in North Kolkata, it's raining heavily and tremendous rain is
And
falling.
ma'am, can you just increase your volume? I mean, it's sounding a little bit low.
Are you able to hear me? I'm on the, yeah.
Audible, ma'am, but slightly the volume can be raised.
Uh, It's already my volume. It's yeah, just
Okay, okay, okay.
yeah.
I think the participants, I hope all of them can hear you.
Okay.
Yeah.
Okay, without wasting any more time, good afternoon to everyone, one and all over there. And it's a great honor to be speaking at this 1 week online faculty development program. And it's a great honor to be a speaker, which is the program which has been organized by Heritage Institute of Technology in Kolkata, and as well as in collaboration with AMIEE Association. I would like to thank all the organizers as well as the program conveners for inviting me to share my insights on optimization techniques in engineering design using genetic algorithm, as well as particle swarm optimization and artificial neural networks. Now, why did I choose to talk on this matter? Because it's a domain where I prefer to talk lot and lot, because it's a domain of my research field. And as engineers and researchers, we are constantly actually solving problems, and optimization is at the heart of engineering innovation today. So today we will be exploring how intelligent algorithms are revolutionizing this entire process. And so first, starting with my slide, let us delve into meta heuristics, which from the backbone of many modern optimization, techniques. What meta heuristics are broadly to speak about are the high level problem independent strategies that are designed to efficiently explore different search area or search spaces. They do this by combining these different lower level heuristics. So heuristics mainly we find in the financial domain, where we apply for finding out the risks or detection of risk, achievement of different techniques like within the portfolios, etc. Here, this high level problem independent strategies, which I mean to say about the meta heuristics, they are designed to achieve a balance between exploration, that is researching the new areas of the solution space, as well as the exploitation, refining different known good solutions. So these methods are incredibly powerful, as well as especially when dealing with complex nonlinear or multi-objective optimization problems. And if we feel like, yes, we need to encounter this to the electrical engineering design, which is the basic interrelationships for this week-long FDP. So it's all about which we can fit into the circuit layouts, power flow control, or fault diagnosis. So there are several major familiarities of meta-heuristic algorithms, and if we find this in the evolutionary algorithms, which has been inspired by the process of natural selection, we can find swarm intelligence techniques, which include this genetic algorithm, differential evolution, and as well as the evolutionary programming, all of which simulate collectively on the collective behavioral pattern of natural systems like flocking of birds or fish schooling. Coming to other types of swarm intelligence like this cooling, which mimics the physical process of heating, slow cooling of metals to remove defects and reach a minimum energy state, as well as which is ideal for escaping local optima. There can be other techniques too, like the taboo search, which I have mentioned over here, and this actually uses memory structures to avoid cycles and guide the search intelligent, by forbidding the different visited solutions. So there can be these different sorts of techniques which can be used within the meta heuristics domain. Now, if we consider these properties of these meta heuristics, as we have already introduced the meta heuristics, so first, the meta heuristics are not direct solvers. Instead, these actually guide the search process, and these procedures intelligently explore the problem search. So this can be done using rules inspired by also rules inspired by society or rules inspired by physics. So unlike exact algorithms, they don't guarantee the global optimum, but aim to find out the high quality near optimal solutions efficiently. And also the key strength of these meta heuristics would be the ability to finding or navigating the complex search spaces. So these meta heuristics can efficiently navigate the complex search spaces, whether it's multidimensional or noisy or non-convex, making them ideal for problem where traditional techniques. Coming to the third one, so these are approximate and non-deterministic. These might give slightly different solutions on different runs, and that's why this design or this randomness helps in escaping local optima or broadening the search areas. So meta heuristics are actually problem independent. Now, if we consider this slide, find there is a quotation. So if you all can draw your attention to this insightful quote on this slide, which actually states about genetic algorithms which are good at taking large potentially spaces and navigating them, looking for optimal combination of things and solutions which one might not otherwise find in a lifetime. And this actually captures the very past essence of genetic algorithm, which is all about like genetic algorithm are inspired by the natural process or procedure of natural selection procedure, which relates to the biological mechanism behind evolution. Now, these actually mimic low nature or, which are evolving organisms to adapt and survive. In the same way, genetic algorithms would actually evolve solutions to optimization problems, generating the different or after one after the other generation, they would actually evolve issues. You can find that yes, this genetic algorithm is been discussed upon. So these are categorized as direct search algorithms, and which actually do means blindly searching the space area. Instead, using any biologically inspired mechanisms to intelligently guide the search towards high quality solutions. Rather, John Holland in 1970s, a professor of University of Michigan, he developed this concept. And his dual motivation was firstly to understand how adaptive procedure could work in natural systems and how organisms would be adapting or evolving into or thriving into. And secondly, it also visions to lead to the development of a class of algorithms that could adapt or learn the things evolving time over. So making this ideal for solving ill-structured or dynamically changing optimization problems. And these are actually efficient or effective. And these are meant for wider range of problems, not just engineering, but also in machine learning, pattern, recognition, data mining, or combinational optimization problems. So it's particularly useful in multi-objective optimization. Even myself within the area of finance, when I applied this in my research domain, initially I started with my research with a single by application of all these meta heuristic techniques. PSO, SEO, and colony optimization, differential evolution. But later on, I also objectified on multi-objectives, that is into the financial domain, finding out the risk and returns, ascertaining risk and returns at the same time. So it's particularly useful in multi-objective organization optimization, sorry, and where trade-offs are required to be balanced across multiple goals. So if we relate to electrical engineering, balancing the cost, efficiency, and safety, it can be used widely into the businesses and science, as well as electrical engineering for designing, controlling, tuning, and reliability enhancement. So, this essence of GA actually serves as a powerful tool that bridges this biology or computation with unmatched versatility across disciplines. If we come to the next slide, see, here we can find out the, different components of GA. Now, let us break down these key components which actually make up GA algorithm. Understanding these elements is very much crucial because each step of this GA procedure would actually correspond to the biological metaphor. And implement a GA, we need a problem to solve, and following components should be looked into. If we find the first component, which I have stated about encoding technique, which actually do mean the gene or the chromosomes. And here the gene or chromosomes, these actually are the foundation. So this technique is the foundation where we must represent the solution in a form that algorithm can manipulate. And like typically like strings or bits or real numbers or permutations, think of this as DNA in a biological system, which each chromosome actually encodes a candidate solution. Each gene represents a variable or trait of the solution. And if you find the next one as the creation, which is the initialization procedure, this actually is the starting point. And this starting point is where an initial population of solutions is randomly or heuristically being generated. So just as nature begins with a diverse gene pool, a good genetic algorithm would actually start with a diverse set of candidate solutions. So this is actually required to ensure a wide exploration over the varied search space. Coming to evaluation function, which is all about the environment, and this is also known to be as fitness function. I hope you all know about this. So this is where each chromosome is evaluated here in genetic algorithm. So how well does this problem actually the solution would perform? And if it is like, so this step actually mirrors testing an organism's adaptability. The better the fitness score would be, the higher would be the chance of being for the reproduction procedure. So coming to the next step, it's all about reproduction. And reproduction, when we state about, so this step actually selects chromosome for crossover based for the fitness. So we have already mentioned about the fitness in the evaluation function. And when it is based on this fitness, as well as the popular selection would be the technique, including like tournament selection or rank-based selection. So it would actually ensure the better performing solutions having this higher probability of passing their traits. And coming to the genetic operators, when mutation, recombination. So this is the crossover mutation function, and where combining of the genes from two parents to produce or more offsprings can happen, or introducing the random changes in the genes, helping the algorithm exploring new areas and maintaining diversity. And whenever we speak this meta heuristics, it really does feel like much interesting, because when we are relating to the real life genetic behavioral pattern of organisms, or like flying behavioral patterns, which will come in the next technique like PSO, or the ant colony optimization, where the behavior of the ants in the search of food can happen. So all this comes into our. So coming to the next one, the parameter settings, which is all about this, practice and art, and it is about the hyper parameters. These elements of the population size, or what we have mentioned in the crossover and mutation rates, or the number of generations, actually does depends on this parameter settings, or the particle and art, which I am mentioning, or which we mention into these components of genetic algorithm. Now, the simple algorithm would actually be considering about the simplified working structure. See here, which actually is in the essence of a loop of evolutionary refinement. And if we go through each step, we can find how the initialization of the population occurs at first, the first step, which is creating the diverse set of initial solutions actually, and usually randomly being generated. So this set would be called to be the population under each member, or the chromosome, which presenting the candidate solution of the problem, or the for this problem, for any of the problem. Now, this population is the next one, where we actually evaluate how good each solution is using as a fitness function. So whatever fitness function we are putting into, that needs to be evaluated, and this is actually determining how likely each chromosome for reproduction. And in engineering application, this could be minimizing the energy loss, maximizing the efficiency, or achieving the cost reduction. So criteria, while termination would not be, this would be the main loop, and this algorithm will continue to evolve the population until the criteria would be met. So until and unless the termination criteria is met, the loop would be continuing. And common stopping criteria would include like the maximum number of generations again, or a solution of acceptable quality which is required by the researcher, or in fact the successive generations over which any improvement can be done. That is, no improvement if it is impossible, or impossible, means if any improvement is impossible over a successive generation, that is been selected. And selecting of the parents for the reproduction would also be the selection of the typically the parents. So here, how the ranking system or rank selection or tournament selection would happen. These are chosen through selection techniques. Combining this all, after the performing this combination and mutation, so crossover and mutation, when it is being done, combining both these two, the evaluating population can be happening. So after the new generation is formed, we can re-evaluate the fitness function again. Function which is which is already been setted, this can be again re-evaluated, and the process actually can be continued with newly evolved the population. So in short, this is actually a loop, and this loop would contain the selection, crossover, mutation, evaluation. These are all mimicking the evolution, and allows the algorithm to iteratively improve towards the optimal or near optimal solution. So once this solution is being reached to, it can be stopped. And in the section, we can also explore the particle sum optimization, which would actually show a very different but equally powerful nature inspired algorithm. Now, coming to this slide, again, when GA cycle of reproduction can be, spoken about, it's all about visualizing the core engine that GA algorithm, and it's all about the cycle of reproduction, where we can find that, yes, which you can find in this slide, it illustrates how the population actually evolves over successive generations. Each block represents a stage, and in the genetic life cycle, the arrows show the flow of individuals, and or the chromosomes. Through this process, how it goes on, we can see that the population at the center of this cycle, you can find the current generation of the candidate solution. This is the population. This is the working pool from which the parents are selected and to which a new offspring can be added or are added. And coming to reproduction, from this population, we can select individuals or one can, this can become, parents. So the selection typically it is biased towards the feature individuals, and this can undergo reproduction, create children using crossover also, and the genetic mixing mechanism would continue. Modification can happen. The newly formed children are then subjected to modification, which actually refers to the mutation process, and this introduces the random variations, sometimes small, sometimes significant, to ensure the population remains, which actually would remain diverse. And coming to evaluation, it is the next modified children which are evaluated using fitness function. So we can assess how well each of them actually solves this problem. So this is critical. It tells us how or which offspring are promising through enough, or these are enough to survive. And back to the population again, if it is been seen, the evaluated children are now ready to re-enter the population. And depending on the selection strategy, they may replace weaker individuals or may be merged with the existing population based on the criteria or the fitness function. And coming to discard, so discard is finally individuals who are not fit enough to have become or which are obsolete, which have become obsolete in the evolving landscape. So these have been discarded, making room for better size and maintaining a manageable population size. So this cycle actually continues generation after generation, and until the algorithm meets its termination condition, this like convergence has been reached or maximum iteration has been reached, this would be continuing. So the essence of GA operates like its self-correcting feedback loop, using like reproduction, variation, and evaluation to gradually improve this quality of solutions. And it's see how beautifully it's described the exploitation of the good solutions and exploration of the new possibilities. No, so a fundamental this is a principle which can underpin all evolutionary algorithm. So if you see the optimization using particle swarm optimization technique, which are latter, which also attention to another fascinating technique, and it is inspired by the genes but also by the social behavioral pattern of the organisms. Now coming to our next slide, we can find the population which actually is stating about the fundamental components of genetic algorithm, and population actually is referring to the set of all the candidate solutions that exist at any given generation. Now each individual to be as chromosomes, and we be representing the potential solutions to the now, the way we represent these chromosomes, their data structure or encoding is very much crucial. And this is crucial because it affects everything from crossover to mutation as well as evaluation. Now, let us look into these common representations of the chromosome. There is the bit strings, and these are the representations which actually sequences zeros and ones, and used often in the simple combinational problems like binary encoded parameters. If we see the real numbers when we are dealing with continuous optimization problems like tuning or controlling tuning a control parameter or designing analog filters, we use these floating point numbers. Example like this, we can 43.33, which we can use. And these partitions of elements, these are like traveling salesman problem or routing this and scheduling, where this order actually matters. And if you consider the list of rules which are useful in the expert systems, the fuzzy logic controllers or rule-based design, where each gene represents a tight, rule. If we consider these program elements in genetic programming, actually chromosomes represent actual program codes, and or we can say about the decision tree. So these are highly expressive but more complex to manage. Example like logic tree, symbolic equations, or flowchart elements. And any other data structure which is been considered, this is all about the flexibility. As this meaningful crossover and mutation operations, we can use any data type or structure, or which would represent the graphs or trees or hybrid encodings, or in fact the matrices. So this is all about this any data structure, and about the choice of encoding depends on the nature of this problem. Whatever the problem is, a well-designed representation makes it very much easier, because for this genetic algorithm to evolve towards better solutions, it facilitates the effective genetic operators, and the evolution actually starts. And yes, it reflects the diversity, drives discovery, as well as it actually ultimately leads to near optimal designs. Now, if we consider the reproduction here in the next slide, it is where the selection it determines which chromosomes would be, which chromosomes from the current population would be selected or chosen to contribute their genetic material to the next generation. And the parents would be, parents are actually been selected from the existing population. So these selected individuals would then undergo the genetic operators like crossover and mutation, as I have already stated, to generate the children or these, offspring solutions. Although the parents are selected randomly, their probability of being selected is not uniform. This is, yes, the technique, and where rather it is by proportions to their fitnesses also. So this process actually ensures the better solutions, having higher chance of being passed on the next generation. So where we can find the entire so a balanced selection strategy, it is all about the modification through crossover and mutation. Coming to the chromosome modification within this genetic algorithm, this stage is the key to introducing the variability or exploration into the search area. And if you can find these, where actually generating new solutions are been happening by altering the genetic materials of the children. So modification module and what comes out of these modified children are ready to be evaluated. How this modification actually happens? Modifications are, stochastic. They are these are probabilistic. In child would have a certain chance of undergoing one or more genetic operations. So there would be mutations, definitely. So this is a random, alteration of one or more genes in the chromosome. And again, it's all about change, flipping, which I have showed in the bit from 0 to 1. So flipping a bit from 0 to 1 would happen. Value in the vector can happen, would be happening along with that. Swapping with the cities in the routing problem. That is what can be happening. So mutation is essential, and coming to or recombination, where this operation combines parts of these two parents of chromosomes. So 1.1 crossover for bit strings, or arithmetic crossover can happen for real valued chromosomes. Yes, for mutations, there can be partially matched crossover. And crossover would actually promote inheritance of group traits, or it would actually accelerate the search toward better regions. In practice, this crossover and mutation are applied selectively. Sorry. If we come to this next slide showing only the mutation function, so we can focus into the different concepts here, like the local modifications being done and local search operators happening. So it performs small or random changes in the chromosomes, and these changes would help in exploring new regions. These now, if you can think of the biologically equivalent or of a like or any copying error or a random gene which can be flip that occasionally, so result would be in favorable trait, right? So for binary representation, mutation involves flipping bits, changing this 0 to a 1 or vice versa, and it can be for this real valued encoding. The mutations may involve adding a small random value to a gene within some defined bounds. For permutations based problems like routing, scheduling, or mutation, this might involve swapping of two elements, like reversing a segment or rotating positions. This can happen, and preventing this, convergence, premature convergence, I would rather say, because it is done for to by ensuring that the population does not become too uniform, or it would be stuck in a local optimum. So it allows the GA to recover if a good solution are lost, or if the population starts converging too quickly without meaningful improvement. This can be, the best way to get equipped from that. So in a broader frame or perspective, this genetic diversity would actually promote adaptability, and it would actually strengthen the algorithm, one algorithm's ability to escape this local optima and continue continue the improving quality of this algorithm. So up next, we will look into the mutate and the crossover also. I'm I'm going over this slide a little fast, because yes, it would take much time if I go into all these slides, into the depth of the slides. So if we consider this crossover or recombination in a fast manner, so it's all about the two parent chromosomes which are selected from the population, usually based on their fitness, and this crossover operator would actually combine portions of both the parents. So there are various types of crossover strategies which would depend on this chromosome representation. For binary strings, a single point crossover would be there. A point is selected on this parent string, and everything after that point is swapped. 2-point crossover can also be there. For real valued chromosome arithmetic crossover, for partially matched like crossover, for this permutation based problem can be happening. So there can be order combination also, so order or cycle crossover. It's very important, because this crossover is the creative engine, and this is the creative engine of this genetic algorithm, which is known in the bookish form, and it is actually generating diversity. And if we find the driving and the search toward the optimal regions or the solution space is happening due to the crossover or recombination. Coming quickly to the next slide, the evaluation, which would actually is stating about assessing the quality of the newly generated offspring. In other words, determining how good a candidate solution can be in solving the problem at a space. So fitness function can be changed. The fitness can be changed and found out that yes, if we can reach to our optimum solution. Coming to the deletion portion, yes, it's the part where we can find that we can actually come with this, essence of deleting or deletion of is all about the pruning of the function, and we can remove the unproductive branches, and we can go so that the algorithm can grow stronger and explore more fruitfully. So we aim to retrain the we can remove the weakest one, and we can maintain an adaptive and we can also evolve the population, or evolving this population would actually get the better or with best gene or best generation, we can find out. Looking into the next one, it's the illustrative example. Actually, it states about the three functions. If you find this behavioral pattern of the birds, it's all about flocking of birds. It's an example where the hoarding is there, the fish schoolings. So it's all about the different behavioral pattern, and it's related to the genetic behavior of them these organisms. Consider these examples. Yes, these are the different example of the problem solutions, and these are the solutions to the problems of the genetic algorithm, which we can find. Quickly running with this, which issues one practitioner can, while being a genetic, algorithm practitioner, what issues can be there. Now, while these algorithms are very much powerful, we know these are also flexible, but practitioners can often face several challenges, like encoding the solution, choosing the right representation, whether binary or real valued, or permutations, or greatly which would be affecting the algorithm's performance. So these can be there. There can be issues designing, with designing the fitness and mislead the search also. Tunings, so population size or the mutation rate can be also a big problem. So there can be also issues which a practitioner can find, and the benefits overall can be the versatility, and this would actually be that GA don't actually require derivative information, making this like non-differentiable, making this a noisy or black box function. So gradient needed over here, and if it is, because it is the global search, it is having global search capability, they would actually explore this, can explore the search space broadly and less likely to get stuck into local optima. Finding this, in short, this flexible, powerful, as well as adaptive, and this can make highly effective, or this can be highly effective for the for solving the real world or high complexity problems. Now, when a researcher or a practitioner would be using these genetic algorithms, now genetic algorithms are not a one size fit, which would fit all the solutions like that. So it can be used when the search space is very large, the problem is very much complex, or it been poorly understood. So especially when traditional method actually struggles over there, finding algorithm can be the efficient solution to that problem. And application of genetic algorithm, so objective function when it is non-linear, when it is discontinuous or multimodal, definitely genetic algorithm can find a solution for that. And yes, conflicting constraints can be there. So whenever one is facing a problem that's very much hard to solve analytically, or too complex or deterministic methods are to be applied, so that's where one can consider this genetic algorithm to be applied. Yes, I'm not going to this portion. So our genetic algorithms, these are, overhyped or not. So a common tongue in cheek like question, this is a question which is always there. So if we can explain this, so it's a beautiful quote which actually captures the real value of GAs, and not in the frame of fortune or yes, but it is the immense practical utility across domains like engineering, finance, biology, or AI, and much more beyond. So this can be applied. So this is the richness which lies in the relevance of GAs. Sorry. Coming to the new slide, new technique. And let's now dive into the second major meta-heuristic technique in our discussion, that is all about the particle swarm optimization. Now, if a genetic algorithm inspired by biological evolution, then this PSO, actually this particle swarm optimization, draws its power from social behavior, which especially from how the swarms in nature operate. Just think of the flocking of birds searching for food, or a school of fish reacting or reacting to the predators. So there's no central leader, yet they move in a highly coordinated and intelligent manner. So PSO is based on the kind of distributed collective intelligence, and it was it's been detected, or it's been brought up by uh, James Kennedy in 1995, and Everhart, an electrical engineer only. Now, coming to our next slide, which actually states about the PSO, and it states that how this PSO particle swarm optimization would actually deal with. So PSO scheme, it's very simple, yet it's very much highly effective also, and it combines with the global exploration and the local exploitation, which allows the swarm to intelligently search for the best solution. And yes, up next we will look into the mathematical equation actually that governs with this behavior. And if we see, you can see here that if you find the best known position, and yes, it speaks about the different bird or a particle or the food or the solution, and it's about the solution or the fitness which has been achieved. Now, a position which is there, which represents the current solution, and a velocity which actually, and a record for the personal based solution is been recorded, or knowledge of the global best been found by ethical. And the representing potential solution would be the flying to the solution space area. So this needs to be adjusted, and its movement is based on the own experience or experience of the other swarms. So the goal is for modeling the social learning, or and applying it to the numerical optimization. These GAs, genetic algorithms, PSO actually does not rely on crossover or mutation. Instead, it models a population of particles, each of which would be representing the potential solution. Now, the PSO scheme, this actually states about the best solution, which I have stated, and the P-based solution, or the which is known to be the particle based, or the other one the position based, and the global. And if we say about these two, so P-based is all about the best known position so far, and adjusting all these positions and velocities over time, it can also find the best position in the entire swarm. So that is all about the global best. And these creates a balance between the individual learning, and balance between the individual learning and as well as the social sharing. Particle updates its velocity based on this P-based and the G-based, and this would actually move into the new position. Now, PSO search scheme would actually state about this global optimization, or global the local optimal values to be found out, and it states about the updating the velocity. See here, when we come to these or two key equations of this, here how the velocity updation is being done. And here we can find that inertia weight, which controls the influence of the pretty exploration. Coming to the C1, 2, this states about the cognitive and social coefficients. So these are all about the random numbers between 0 to 1. And 0 and 1, yes, these random numbers are being selected, and the best position, P-based or I-based, is also been found out. And after that, the global based solution can be evaluated. So it's own learning, and it's about the group learning. So P-based would be about the own learning, and the groups learning about the G-based, and where the randoms would be avoiding getting stuck. So this is the B. And position update would be happening in both the cases. So this is how these two equations together would be guiding the entire swarm through the space search and search space, and balancing the exploration or exploitation area. And inertia weight would actually play a critical role. So inertia weight would be this, which would be here, which would be encouraging the exploration, and if it is been lower, it would be encouraging the fine tuning or exploitation. So in many versions, this W is dynamically adjusted during the run for better control. So this is simple, yet very fast adaptable also. So here we can find that how the is been done first. This algorithm would be step by step. It states about this how initially the swarm initialization of this swarm is done when we begin by randomly initializing the position and velocities of these particles in the search space. Then how the evaluation is being done. So how the fitness is being computed of each particle objective function which we have created based is also been done, and based is done. Each particle when been updated with its personal base position, and the swarm tracks, so swarm would be tracking the global base position. Updating of the velocity would also be done using the particle updating equation. So we would be calculating the new velocity and updating the position of each particle, and finally the repetition would also done. So here in short, this PSO is all about the loop, evaluating, updating, moving it, repeat itself. So it would be done in a dynamic manner, adapting to the learns from both the individual experiences or the collective wisdom also. So this application would be all about it can also explore some many or vital applications can be done in the electrical engineering also. So how it could be done, I will state about that. So I would quickly skip this clustering algorithm, which actually states about each particle, how this represents a set of cluster or centroids. The goal of this to optimize the centroid so that the intra-cluster distance has been minimized. I would rather, I'm skipping this, and how the achievement of the experimental results is done. Here is once the PSO algorithm has been implemented, we run multiple experiments to test its performance, and these are been done in the convergence by convergence speed or accuracy of the solution is being maintained, and we compare the results against the benchmark or other algorithms to validate the effectiveness of the PSO in solving the target problem. Now, there are also certain issues I have stated for the practitioners, which while using the GA also. So while PSO is very much simple, as I have stated, and effective, but practitioners may also face some challenges like premature convergence or parameter sensibility, like using the inertia weight or learning factors. And yes, careful tuning and hybrid approaches are often required to overcome these limitations. Now, certain benefits for usage of these PSO algorithms, because PSO particle sum optimization actually do offer several compelling advantages. like PSO is very easy to implement with just two main equations, as I've stated, for velocity and position updates, and fewer parameters to tune. This can be applied, and these have very fast convergence rate also, where we can find that PSO often in continuous and real valued optimization problems, and it's very much flexible enough and scalable. So it's a robust procedure. In overall, it's efficient and versatile also as an optimization technique, and it's well suited for both this academic research or real world engineering problems. Now, the artificial neural networks. So now we have inspired optimization through genetic algorithms and particle. Shift our focus to the third pillar of this session, and it's all about artificial neural network. Simply to put, these artificial neural networks are computational models, which actually is inspired by the structure and functioning of the human brain. So these are designed to recognize patterns, learn decisions, even in complex nonlinear environments. Just like our brain learns from the different experience by strengthening certain neural connections, artificial neural networks learn from data by adjusting internal parameters like the weights. And there can be the input layer where we feed in our features or the data itself. There can be the hidden layers where actually the learning and transformation is taking place, the outer layer which delivers the final or the classification of result is being done. So each unit in this network is called neuron, and every neurons has an associated weight. So because this, unlike traditional algorithms, this artificial neural network don't require explicit programming. So they learn from examples. This particularly it is useful in function approximation, series forecasting, pattern recognition, control systems. There it can be applied, and in context to electrical engineering, this artificial neural network also been successfully applied in cases of load and energy demand forecasting, fault detection, classification in power system. So this has been done, or controller design for dynamic systems. So in short, wherever prediction, control, or classification is required in a complex environment, artificial neural network can be a perfect choice. Yes. So applications, as I've said, where it can be applied, it can be most widely tooled across various disciplines, not only yes, it can be across the disciplines due to their exceptional learning and generalization abilities. And it can be, if we in the allied domains like electrical engineering, it can be load forecasting and energy demand prediction process. Also, one of the most critical challenges, power systems, where actually the accurately forecasting is being load. So artificial neural network are trained on historical consumption data and external variables like temperature or time to predict future demand can be done. This can be done by enabling the efficient management or this reproduced operational. Next slide, we can find the different models of artificial neural networks. And artificial neural networks actually come in various architectural models. These are suited for different types of problems. This can be feed-forward network problem, neural problem, or this can be recurrent neural network. Information flows in one direction from this input, where this can be widely used in regression and classification, which can be stated to be as feed network. And it can be so the problem where each model has unique strengths, and is chosen based on the nature of the data. And so this conventional neural network which has been originally used in image processing, but now applied in power grid monitoring also, also, or is also. And if we think about the neural network, so it can happen where they have the feedback loops and allow the memory of previous inputs, so which is ideal for the application of load forecasting or signal prediction happen over there. Now, neural network. This neural network is a computational model and which is inspired by the human brain, as I have stated. It consists of the interconnected layers of nodes, or which is also known to be as neurons, that work together, to process as well as learn from the data. So each neuron receives inputs which applies the weights, which passes through that like activation function and also layer. And if we find the biological neural network, we can find, before we dive deeper into this problem, the biological neural network between or behind the artificial neural network. So how it has been evaluated, a journey which has come to span over several decades of it. How this artificial network and biological neural network can be related, it's been shown. And the application of this neural network, artificial neural network, can be done in load forecasting, like power demand using historical data, or fault diagnosis, like classifying the and detecting the equipment's failure in real time. Now, this I will also explain in my later slides. Going closely to the end, because I understand time comes. Now, how this application can be done into electrical engineering. So as I have already mentioned here in my lecture session, that artificial neural network can be applied for load forecasting, predicting short-term and long-term energy demand. This can also happen or it can be applied in fault detection or diagnosis for classifying and locating the faults in transformers or lines or motors. And it can be done for adaptive like controlling system, implementing neural based controllers for dynamic systems. So this can for the different segments, like renewable energy forecasting can be done, predicting the solar irradiance or the wind speeds to optimize or integrate. So the integration procedure optimization of this can be done. The power quality monitoring, like the identifying the disturbance like sags, swells, or harmonies in time, this can also be done. So yes, this can be applied. And if we application of genetic algorithm, so genetic algorithm is also, it can be related or it can be applied in the engineering, electrical engineering especially. So here also the reactive power control, which is a major issue in smooth flow of the electrical power, both at the distribution side as well as transmission side. This can be handled, and many artificial intelligence techniques or this can also be used or put into use for controlling this reactive power through this application of GA. And power flow can be, yes, definitely it can, which can be considered as to minimize. Next, and we can also find this objective function being represented by the generation of the loss or the generation cost, and GA or genetic algorithm, which stands to be the best technique for solving the optimization technique when been compared to the conventional or traditional methods. And when we find this PSO, particle sum optimization, it is how, or it can be absolutely fitting to the electrical engineering disciplines, while the economic dispatch, method comes into use, minimizing the fuel cost while meeting demand, or the PI improving the control system response. In fact, the microgrid management can also happen, balancing the cost, or power flow in the distributed systems can also happen. So yes, optimal control variables or for efficiency and stability can be done by application of these particle sum optimization. And it's really very interesting that we can the behavioral patterns of these birds, flocking of birds, or fish schooling of the fish, or the behavioral patterns of any other organisms, and the GAs or neural network, how this can be applied into the different fields, not only in the field of computational science, but also in the allied disciplines, and as well as in electrical engineering. So I would mention about the electrical engineering because today we are having this FDP for 1 week long time aimed or targeted for the electrical engineering section. Or myself being into the field of the computer science, I related my basic all this knowledge or knowledge of meta heuristics to the field of finance. Basically, in today it's been used for identification of the risk amount in the different portfolios. So finding the optimal values of risk being allocated in the portfolios, it was my target area. So how it apply to different other fields is being stated. So we are almost into the end of the session. I hope, yeah, the organizers here are present. Yes, if there is any question, I can take those.
Thank you, Madam. Participants, do you have any questions, please? You can also write your questions in the chat box.
Madam, I have one question. Am I audible?
Yes, sir. Yes, sir.
Differential evaluation is in what you have seen here. Differential evaluation.
I am not able to yeah.
Ma'am, can you hear? Actually, I'm also hear a distorted version. I think the network connection is not good. So, ma'am, can you have you heard the question, ma'am, properly?
Differential evaluation.
And even my connection is very, very poor.
Yeah. Sir, can you write the question in the chat box, please?
Okay, madam.
Yeah. Hello.
Yes, sir. Sir, have you written the question? Differential evolution in AI applied to EE. Sir, is that your question?
Yes, madam. Yes, madam.
Navamita, can you relate?
I cannot, yes, I cannot hear, but I cannot make out the thing that is written in the chat box, ma'am. Can you get it? Differential evolution in AI applied to EE.
Role of differential evolution?
Maybe, I suppose. Because I also cannot hear anything. So can you write in detail? I mean, is it a question like whole?
Evolution, how it's about.
Yes, yes, yes. I think so.
Yes.
Sir, are you there? Dr. Shrikant, are you there? Hello? Any work area? Okay.
Navamita, what I found that he was asking regarding differential evolution. Yes, it's one other important technique. I would rather try to say about a little about that. It's another metaheuristic technique, you know, about the differential evolution, which is solve different complex efficiently exploring the search spaces and converging to the near optimal solutions again, even in the face of like challenging lives. Now, as we were talking rhythm, PSO, and artificial neural network, the simplicity here or robustness would be various domains and yes, DE is it can handle the wide range of problems, and it is very much efficient enough in the between the vectors for mutation and enabling it to explore the search space areas effectively. For genetic algorithm, we had all the code, starting from the generation of the population and last to the deletion. But here we have, yes, D would be successfully applied into the diverse fields. For mutation would be enabling it for effectively, and also the solution relatively or very quick. Sir, this D differential evolution, it's all about yeah, definitely. It's also a tool for optimization challenges where the best possible solutions can be found within a given set of the constraints. And D again, I would say, because I'm very much interested to state about this. PSO, SEO, GA, D was also a where the optimal for finding the optimal solution applied in my research domain. Yes. Yes, sir. Yes, Navamita.
Thank you, madam.
Ma'am has written, yeah, ma'am, Madam Pramani, she has written for transforming evaluation to GA in the chat box. I mean,
yes, yes. Tell me.
Ma'am, can you see the chat box, ma'am? It's written for transforming evaluation to GA.
Transforming?
Evaluation
to
GA.
Into GA.
She has not written anything else. Could you please name some AI tools
evaluation
for transforming evaluation to GA?
Some techniques you require, or what she is telling?
Some AI tools. AI tools.
Oh, some AI tools. Okay, okay. If we find some different techniques, could actually transform the evaluation to GA. So this can be like, yeah, like we can be there. We already know evaluations and transforming the I can artificial intelligence, how it can be created for unparalleled opportunities, which actually would simultaneously relate to different problems. So this can also happen. And it can also be there using, posing the different new risks for all the organizations. This can be, yeah. And some different tools can also speed the, increase the efficiency or remove the bias, improving the trust procedure of the natural language problems can also be happening. So analyzing the different, uh, context, we can form the tracking progress. So AI can actually accelerate the planning and the formulation of the evaluations, right? So it can support the analysis of different interventions into context and help out these challenges as well as the risk linked with the program. So this can along with knowledge sharing or be the knowledge sharing innovation technique, or it can be the recommended systems for disseminating evaluation, for finding this, stake queries can be resolved. So this can also be done.
I think, ma'am, that's it. I think we have answered the questions much in detail. Thank you, madam, for your wonderful presentation. And once again, you have explained the algorithms of PSO and GA in detail. So thank you, madam, once again.
This can be, Navamita, these different algorithms. It's not very much such small sessions. I hope you understand.
Yes, we will look forward to more such sessions with you, ma'am.
Yeah,
I know it's a vast topic.
on entire, this technique to be discussed upon, it requires huge time. Maybe an entire session is required to discuss
Right.
one technique. So
Yes, ma'am. We'll definitely plan more such sessions. So it occurred to me. I mean, for this FTP, it occurred to me.
Yes.
It's application in electrical engineering. So I would definitely look forward to some more areas and some other titles of future FDPs, and definitely you would be our coveted speaker then. And thank you, madam. And once again, with this I conclude this FDP, 5-day FDP. I am thankful to all the participants who have made this FDP successful, and of course the speakers who have made their deliberations and shown the expertise. I am thankful to my organization, my head of the department, Professor Dr. Shoibal Dotto, for being with me in organizing this program, for giving their support. I am thankful to my organizational CEO, Mr. Pradeep Agarwal, and Professor Bashuk Chaudhary, our principal, for their continuous motivation in organizing these programs. And of course, I'm grateful to our joint administrator admin, Mr. Arvind Srivastav, who has extended his help always in every aspect. And I am thankful to the IQAC cell for its support, and the IIC convener, Mr. Nandan Jana, who has always cooperated me in whichever way I have asked for help. So once again, I express my gratitude for all, and I look forward more such sessions. And lastly, I'm thankful to the association, AMIEE Association, without whom this program would not have been possible. And so we look forward to more such programs with AMIEE Association and the Electrical Engineering Department of Heritage Institute of Technology. So with this, I conclude this 5-day FDP. So it was a nice, enriching experience with you. So goodbye. So I must say good night to you because it's evening now. Okay, so bye. I'm closing the session. Thank you, ma'am, and thank you, Dr. Shrikant. As I can see, you're still there.
Yes, Navamita, thank you so much. So yeah, it's time to leave, and thanks to all the organizers.
Yeah. Look forward to see you, ma'am. You're in my hometown.
Yeah. Definitely. Sure, Navamita. Thank you.
Okay. Bye, ma'am. Okay.
Yeah, bye, everyone.
Okay, so leaving the session. Okay. So bye all. Goodbye to all.